Hi, welcome to lesson 3.2, Maxima and Minima. As you remember from yesterday, we determined where the functions were increasing or decreasing. Today we're going to determine where functions have maxima and minima values, which will help us determine where the turning points of a graph of a function are located, so our curve sketching can be done more precisely. Okay, so we'd like to identify the maximum and minimum points on this graph. So obviously if we take a look now, if this is a closed interval, meaning that there is no arrowhead at this point or this point, meaning that the graph just stops here at some value, we can say that perhaps it stops at some value A and continues on until some other value B, x values. And then, so this could be a maximum value or a maximum point. This could also be, sorry, that's a minimum point here. Here's a maximum point. Here's a maximum point. And then we've got minimum points, which would be this point here, and this point here. So these ones, which we're going to see in a couple seconds, correspond with some sort of x value called C, and you'll see why they're labeled with C in a second. Obviously they're not all the same value, as you can tell, but we just call these x values C for now. So if we want to define local maximum and minimum values, or turning points, it follows a little like this. So a local maximum or minimum occurs when the function changes from increasing to decreasing, or vice versa, which means that the derivative must change sign from positive to negative at these points, where of course at these points the derivative must be 0. So if we take a look over here where the graph is increasing and then it changes to decreasing, and at this point there is the derivative of 0. Here the derivative is positive, here the derivative is negative. Again, the same sort of thing happens here. The graph is increasing where the derivative is positive, decreasing, the derivative is negative, because the derivative is the instantaneous rate of change, or the slope of the tangent. And so the slope of the tangent here would be positive, the slope of the tangent here would be negative, and right at that maximum the derivative is 0, where there's the slope is neither positive nor negative. And then of course with the vice versa part of this, talking about minimums, local minimum, we see that the function is decreasing, which means that the slope of the tangent is negative, so the derivative is negative. Here the function is increasing, so the slope of the tangent is positive, so the derivative is positive, and right there the derivative has a slope of 0, meaning that it's neither increasing nor decreasing. And of course we can do the same thing here. The function is decreasing, the derivative is negative. Here the function is increasing, the slope of the tangent is positive, so the derivative is positive, and right here the derivative is 0, meaning the rate of change, or the slope of the tangent at this point is 0, meaning horizontal tangent. So those are all local maxima and local minima. Local meaning where they're changing from negative to positive or positive to negative. So a function f has a local maximum at c, some x value of c, hence the c that we wrote here earlier. If f of c, the y value, when the function is evaluated at c, is greater than or equal to f of x for all x sufficiently close to c. So all the y values evaluated for all x values that are close to c, they're all going to be less than the y value that's evaluated, when the function is evaluated at the x value of c. So this y value here, evaluated at c, is greater than all the y values evaluated at x values close to c. Okay, so that's the maximum value of all y values in this general vicinity here. And the same thing would go for here. When we talk about local minimum, the same sort of idea. Function is a local minimum at c if f of c, the function evaluated at the value of c, is less than or equal to all all y values evaluate all x sufficiently close to c. So again, this is a local minimum and this is a local minimum when the function f is evaluated at x value of c compared to all the y values when evaluated for x values very close to c. So the y value at c is less than all the y values for all the x values in that general vicinity. And same thing goes for this general area here. So those are both local minima. Definition of a critical number of a polynomial function. For any polynomial function f of x, a point on the graph of the function where f prime of x is 0 is a critical point. So a polynomial function, there will be a point, so that's an xy, an ordered pair on the graph where f prime of x is 0. That's a critical point. A critical number is the number c, or the x value of c, in the domain of f of x such that f prime of c equals 0. The critical number is the x-coordinate of the point which gives the critical point. So that's why up here we labeled all of these as c's, because that's the critical number. These x values are the critical numbers producing the critical points, which are where the derivative evaluated at c equals 0. So we get the horizontal tangents. So we will see later, in a couple lessons perhaps, that a maximum or a minimum applies that the derivative is 0, but the derivative does not always mean a maximum. So a derivative of 0 does not always mean a maximum, but the maximum does imply a derivative of 0. Okay, you'll see that in a day or two. The procedure for finding absolute extrema on a closed interval where a is less than or equal to x, less than or equal to b. Hence that's why we chose a and b for these endpoints here, because it's a closed interval. So we're going to determine f prime of x and find all critical numbers of f on the interval. So that means that we're going to locate where f prime of x is 0 and locate all these c values where when we evaluate f prime of c we get 0. So we're going to find the derivative and then locate all the critical numbers, so all the x values that give us a slope of 0. Then we're going to evaluate the function f at the two endpoints, a and b, and at each critical number. So all of these c values that we find for all the places where the derivative is 0, we're going to evaluate the function, the original function, at all of those points, all those x values, and then we're going to compare the values found in step 2. So that step. So we're going to see that the largest value is an absolute maximum, and the smallest value is the absolute minimum. And all values where we have a critical number, those are all local maximum or minimum.